Okay, so suppose that f of xy is given, and as a number of Lego pieces stacked up at the point xy, and you can see the picture of this. Hope this is clear, and I think this is about the best way to illustrate the multi-variable integration, or sometimes called multiple integration. All right, so f of xy is the number of Lego pieces stacked up at each point xy, right? So and then the question is, okay, if you're integrating over this entire, what appears to be a square or rectangular domain, basically the question is how many Lego pieces are there altogether, all right? Now there are two ways to calculate this, or there are maybe more than two ways, right? But two systematic ways of calculating this. And here's method one. Pick fixed x1. Let's say for x1, I pick 6, all right? And then what I can do is to go through all of these points, all of these towers in this row, x is equal to 6, all right? So I have this stack here, this stack here, this stack here, and count all of the pieces, Lego pieces along the line, x is equal to 6, right? And in the sense, in the continuous case, what we'll be doing is adding up all of these towers, and therefore it just becomes sort of like a slice, right? It is like if these numbers are continuous, if these towers are continuously right next to each other, basically what you'll see now is a wall of different height, where the height is representing the the number of Lego pieces. Okay, so it'll be like the area of the height for each area of this slice for each xi, and then because I have x, so for each x, I have found this sum, which is the sum of f of xi comma y. And I add up all the y values from this point to this point, and find out the number of Lego pieces along the line x is equal to 6. All right, then you add up, speed up, and this is wrong. This is in the x direction. Okay, so now we are going to add all of these slices from x is equal to 0 to 10, right? So you integrate along the y first and then x next. That's what I'm trying to say. But in this case, of course, you are adding in the, for each x value, I'm adding in the y direction first, and then you are adding in the x direction. So this is what I am trying to say here, okay? So the first thing you do is for each xi, you're adding in the y direction. And once you have a bunch of these x slices, you add up all these x slices, right? So that's one way to do that. And of course, method 2 is the other way, right? So for each, so this time I'm going to fix a particular y. And by the way, I apologize, but the way this comes out, normally, you do x this way, y this way, z this way. I am turning this around in order to make this an easier to understand illustration. So I am making this x and y goes in the other direction. All right, so take this, rotate this by 90 degrees, and you can imagine this frame, right? Okay, so for this one, let's say you pick y, I fix at this point, right? And so here is the tower representing the point. What is that point? Let's say y is like 5. It's 0, 5 is this point, right? And then as you go along here, you pick all these towers, and you get, let's see, the last tower looks like maybe this one here. Right? You take all these Lego pieces along the line y is equal to 5, for instance. Okay, it's too hard to see here. Maybe it's 5. And so if you pick, and so you can pick all of these points, all of these towers, all of these Lego pieces where y is equal to 5, collect them together, count or add, all right? And that number will be the sum of f of x comma yi, where in this particular case, yi is equal to 5. All right, now you have a bunch of these y pieces, okay? And they all look like this. They all look like, this slice, right? We can call them white slices. And then you add up, again, this is wrong. You add up in the y direction because you have a bunch of y pieces, and then you sweep through along this line y, right? And so what you will end up here is, first you sweep through the x for each x, so for each y value, like y sub I, you fix y sub I, and then you sweep along the x direction to add up all these Lego pieces along that particular y point, yi. In this situation, or in this illustration, it's 5. And then, okay, so that's a addition in the x direction. And then once you have a bunch of these y pieces, for each y, you sweep through, or you go along and collecting all those numbers. So that would be in the y direction, all right? So I call them sweeping through, because you're basically sort of like taking a broom and sweeping through and collecting and counting all the Lego pieces along in the y-axis. All right, so then of course you can see this and this, we're counting the same number of objects, right? We're talking, both of these should represent the same number of Lego pieces. Every Lego piece you see here is what you're collecting. And so the answer is these have to be the same, okay? And in fact, these are the same in a discrete case that you see here. And in the continuous case, we will find, thanks to an Italian mathematician named, let's see, Tonelli, right? Well, Fubini and Tonelli, both of them, you will see that the integrals are going to be equal to each other. Now, this is very much analogous to a very simple case like this, right? So this is something you want to keep in mind as you talk about the two methods or two directions or two orders of integration. All right, so let's say you have two classes, morning and afternoon classes, who took the same test. In the morning, 7 passed and 3 failed. Total, 10 people took the test in the morning. In the PM, the afternoon class, a better class, obviously, 10 students passed, 2 failed. That's 12 students taking the test. Altogether, you had 22 students take the test, right? What we just did is to sort of did in one of these, method 1 or method 2. The other way is to find the number of people who passed, that's 17 and 5, and then you add up these numbers, and of course that's 22. See, it doesn't matter which order you add these. The total answer would be the same, whether you do it this way or this way, okay? So that is how we are going to define the total or the double integral over a region D. All right, and we will start but with a rectangular region in section 1. All right, but because we are talking about integrals in general, okay, I want to just go ahead and explain this. What happens if you don't want to find the total sum of all of these Lego pieces? Let's say you, and this is a vision from the top. Let's say you have this curve C, okay, which is represented by this curve C on the XY plane here, and you have this tower here, this tower here, this tower here, so every point in this, on this curve has a number associated with it, which is the number of Lego pieces at this point, this point, this point, at every single point, okay? Then what do we mean by this? Okay, and we use not dx or dy, we use ds, which is to be described later in the next chapter, actually. All right, so this is called the line integral. I know it's technically should be called the curve integral, but since curves are like lines, we call these line integrals, okay? And so the line integral, of course, should be the total number of Lego pieces. Now, remember, I'm sticking to the analogy of Lego pieces. When we define this in chapter 6, we will not be referring to Lego pieces, but if you are assuming that the f of xy is the number of Lego pieces stacked up at point xy, this will give you the total number of Lego pieces on the curve C, only on the curve C, okay? And we will find, we'll find out how to evaluate this kind of thing. Okay, but this is not coming up until 6.2 because this is actually, this turns out to be a little more difficult than just adding up the Lego pieces in the rectangular region or even any other region. All right, so that's the discrete illustration of what happens in multivariable functions, right? Now let's go to continuous version, which is what we are after. All right, so the continuous version looks like this. So you have z, which is a function of x and y. Okay, you ready for this? right? What did I have here? Okay, so the first thing here is I have picked this point. Oh, by the way, this is back to the usual orientation. X going in this direction, Y is in this direction, Z is in this direction, right? So it looks like I have fixed a particular Y value I in here, okay? So pick a fixed YI on the Y-axis. And what does this region represent? This region, of course, you're integrating now in, in this direction from A to B, right? And so this will be A to B of fx comma yi dx. Remember here, you're finding this thing here, right? And then, okay, so this will be the area of the yi slice. Think of this as a slice of cheese. You have this big chunk of cheese, and I hate to say you're cutting the cheese, but you're cutting the slice, right, of that cheese in this direction. So what you'll get is a slice, maybe try to make it thicker so it looks like a slice of cheese, right? So that's a slice of cheese. And what's the volume, or what's the area of this slice? If you think of a slice as infinitesimally thin, it's basically the area of that. And that's what this represents for that particular point yi, okay? And then we do it the other way, right? You add up all the areas of these slices, right? So then we sweep in the y direction. So what does it mean? We are going to add up the areas of all of these slices. And so what you get is, remember, this f of x comma yi dx. That's what you had. And then you are going to sweep it through in all of these directions from, well, in this direction from y is equal to c to y is equal to d. So now we are going to do c to d dy. Okay, does this make sense? I know it's the first time you saw a double integral. You've never seen, these integral signs twice or two appearing in a row, but that's what you will be seeing for the rest of this semester or for a while. All right, so this is the part you do inside. This is what you did first to find, yi, and then you are now adding in the y direction as you go from C to D, all of the areas of these slices, right? So this is the total number, and this is called the double integral. Okay, and if this region is called D, this is the double integral of D, F, over D and FA. Okay, so that is of course, the volume of the solid underneath of that function Z. All right, but you can do it the other way, right? So pick a fixed, and I mean, this is going to be almost identical to what I described here up on the top. So it should be easy. Pick a fixed xi on the x-axis. So what does that look like in here? Maybe you can draw a picture of it and you can compare yours with mine. I've already done mine, but this, so here, let's pick this point xi on the x direction. And so this is the xi piece. Again, if you think of this as a slice of cheese, you have this delicious looking slice of cheese. Okay, and it's big. It's a big piece, right? Well, I don't know. All right, so that would be f of, and again, this goes from C to D of fxi. Right? Remember here, x is fixed. Right? X is fixed as xi, and then you integrate with respect to y from C to D. Okay, that is the area. So this is, find this. That's the area of the xi slice. Okay, that's what it is. And then what you do is you sweep, you keep collecting a bunch of these slices. In fact, there are infinitely many of them in the x direction from A to B. right? So then you will get, remember what you found first is xi, the xi slice, which looks like this, all right? And then slice, and then you integrate from a to b in the x direction. All right, and the point is, this is also the same value because all we are doing is adding in the different order, but you're adding the same number of Lego pieces, if you like, right? So that is the definition that we will give of the double integral over the region. Okay, so I hope this has been clear. And we talked about what an integral is. It's continuous addition. And we applied the same idea to double integrals. Right, and then we will refer to this again in the lesson on the section, but Fubini's theorem, Fubini is this mathematician who came up with this. The fact that the order doesn't matter, and he proved this with a careful proof, but regardless of where you do f in the order dx dy or dy dx, the order doesn't matter because you are calculating, you are adding up the same number of things, same number of Lego pieces, just in different ways. Okay, but of course this is a continuous function, a continuous integrals, and so the proof would be much more difficult, and we will not go over the proof, but the result is it doesn't matter which order, you are going to get the same answer in either way. All right, I have a couple more things to say about this, so let me do that quickly before we finish this video. Okay, so just so you know what's coming, what happens if you add another dimension to it? If you have a function of 3 variables, x, y, and z, notice here I can't even graph this, right? Because the real value, the f of x, y, z will be in a 4th dimension, and I can't draw that, right? So the best I can do is to say, let's say f of x, y, z is given over this solid E, right? So the solid E looks like this, maybe a stone or some kind of boulder looking thing. Now remember, at every point x, y, z, inside and on this solid, right, you have a function defined. Maybe it's a temperature at x, y, z. Maybe it's a density at x, y, z. Maybe it's the pressure at the point x, y, z, whatever, okay? You can define the triple integral, and dv, so what you do is you partition this solid into a bunch of small rocks, small pieces, small cubes. And so the volume, the dv will be dz dy dx or dx dy dz or any of the 6 permutations of dx dy and dz. And so that's what dv is. But you can define this in the same way. The order doesn't matter. You can do it in this way or dx dz dy or in any other permutation of this. The order doesn't matter. But if f happens to be the density at point x, y, z, remember what it means to add all the density at every single point. And of course, if you have a finite number of solids, these subcubes or something, then you can do finite sum, and that's a finite Riemann sum. But that, if you take the limit, will become the continuous addition, right? Which is your integral. And so this, if f of xyz is the density at xyz, then the continuous sum of all of these will be the total what? Mass. Okay. We talked about the weight, and this was like a pound per foot in our first example. And now you can think of this as a pound per cubic inch or something, right? And it'll give you the total weight. If it's density, then you get the total mass of this. So there actually is a meaning for the triple integral as well. Fine. Yeah, by the way, this we will talk about this in this chapter. In the next chapter, we will also talk about a surface integral, right? So what happens, just like when you had a curve, so where is that? If you have a curve on the plane, you can define the line integral. If you have a surface in a 3-dimensional space, right, then you can talk about this integral over the surface. And of course, every point on the surface is a point x, y, z, and you have a number defined at every point x, y, z on surface S. So in this case, though, what we will do, and we'll define what ds is, right? what we do is at this point, every point on the surface S has a value. When you integrate this, okay, and you can integrate this either on, well, you can't use dx and dy anymore. This has to be defined carefully. But if f is the density function, then of course, this integral is the total mass of this surface S, right? And so, and we will be talking about this. And by the way, we are assuming again that every point has a real value identified with it, right? One of the things we will do is to see the penetration or a flow of fluid across S, right? And the flow will be described by these vectors, right? And then you have to take the normal component of the vector because that is the value assigned for penetration or the transition from one side to the other at each point S. And so you will be given the value at each of these points. And when you integrate this, it'll give you the total flow across S, total penetration or total transfer of the fluid from one side to the other, okay? And that is known as the flux function. All right, so we have lots of things coming up. This last thing is not in this chapter yet, okay? So we'll be talking about all kinds of integrals from this point on, but you really need to understand what integration is in the first place, and that has been the point of this video. Okay, so from now on, if I ask you, what is integration? What are you gonna say? You'll say, it is a continuous version of addition, or you can say simply continuous addition or a continuous sum, right? So what used to be discrete, like adding 1 plus 2 plus 3 is equal to 6. Now we have a function defined on every single point, and you have infinitely many points because every interval has infinitely many points, right? And you take the limit of the Riemann sum, you don't even have to describe it that way. But if I say, add up all these numbers defined at every single point x, and the value defined at x is called f of x. If you add up all of these points at every single point, what do you get? You say it's an integral because an integral is a continuous sum. Right? Notice here, I haven't even talked about antiderivatives. I haven't even talked about how to find the value of the integral, right? Yeah, because that fundamental theorem of calculus is what gives us a way to find that. Okay, and I haven't talked about this because in this video, I talked about what an integral is, okay? And it is the finite or the continuous version of the sum. How you evaluate this depends on that theorem that somebody proved, Newton and Leibniz, which is called the fundamental theorem of calculus, which brings us to the idea of antiderivatives, right? And by the way, that just tells you that integration is the opposite of differentiation, right? And that's really what the fundamental theorem says. Okay? But what is an integral? It is not an antiderivative. That fact comes by the theorem, okay? What is an integral? It turns out to be the area under the curve or the volume under the surface or the total mass of an object, okay? You can describe it that way, but it is the sum. That's what's important, okay? So what in the world is an integral? It is a continuous sum, or you can say a continuous version of addition. Keep that in mind for the next couple of months and you will be fine. All right, I'll talk to you later. Bye.